speak relatively slow because interpreters has to translate for some of you who have phones, and it's not easy job to do in being an interpreter. So it's mostly about graphene, but when someone wins a Nobel Prize, usually a couple of questions arise, how and why. You should actually look more on the screen rather than onto me, because most information will come out of there. So I'll tell you a story behind, and then I'll tell you in the second part of the talk what is so special about this new kind of materials. When I got my first tenured position, it was in the Netherlands. I was doing some experiment in so-called quantum condensed matter physics, superconductivity, quantum Hall effect, mesoscopic. Those terms, if I would start talking today about this research, you would fall asleep after 5 minutes, let me assure you. So it's professional research, but very narrow research. So at the same time, doing my main research, which I was paid for, I was thinking, what else can I do? Something simple, using the facilities. And one of those stories which came along is kind of famous. It's the story about magnetic water, a phenomenon of magnetic water. How it started. Some of you might heard about that if you put a magnet on your tap, this water, which hot water comes through, then there is no question was if this small magnetic fields create such a dramatic effect on water, what would happen if you increase field by a factor of 100? Surprisingly, no one asked this question before. The legend goes, I went into the lab late at night, Friday night apparently, and pour water inside the station in there, like there is a anti-gravity machine. Water compensates the magnetic field compensates the gravity in water, and in addition, it allows this kind of stable, freely levitation of water. The ball is moving because it's intentionally, because it's a video, you would like to see something moving. I'm pretty well educated during my university years, so I of course realized quite quickly that it's not new anti-gravity device, it's just a phenomenon which is called diamagnetism, known to the humanity for 100 years before. There is subtle physics involved, how and why water stably levitates, but as concerns compensation of gravity by subtle repulsive magnetism has been known before. So I'm not going to go into details there about physics which is involved. The biggest surprise came to me is that my colleagues didn't believe that it happened. So a week after jokes, they say I'm pulling their leg, as they say in English. I'm joking, it's a hoax. There was no video to show, it was just my words. I have to do this experiment again. And people were amazed. So they start bringing all sorts of objects which you can put in the magnet. Everything went there, from paper, wood, and so on. And for a month or two, people from all over the world, as far as the United States and Malaysia and Australia, came to put something in the magnet to see whether it's true or not. So at a certain moment I got fed up and I make a picture. It was nearly 30 years ago, so 25 years ago, it was hard to make. There was it pulls your fingers away. It slightly repulses you. So this phenomena is in many textbooks for undergraduate, postgraduate, school kids who learn that we all a little bit magnetic and that we all can be repelled a little bit by magnetic field. Sometimes I go to a conference and person in a corridor meets me and saying, "Oh, I know you." I roll my eyes, and then the person gives me the best compliment possible. I have no idea what graphene is, your graphena is, but your frog. So it has quite a big impact, I would say. And sometimes I get this fan mail, I put it here, it's nearly 20 years old, and it reads, "I'm 9 years old and I want to become a scientist." So I received Ig Nobel Prize for this work together with some other already at that time famous scientists, but I think this letter rests my case that it was worth doing this kind of experiments. When you learn how into something which you have never dealt before. As I told, I'm quantum condensed matter physicist, very obscure area of research, which wins a lot of prizes, actually. A lot of Nobel Prizes went into this area. Probably every third year goes into this area of research. But you want to do something simple. And I learned probably about 20 years ago how geckos climb the walls. Their toes are covered with tiny hairs. When you have anything, or just touch your fingers together, there is so-called van der Waals force, which acts between all the objects. It's very small force. If you pull your hair and touch opposite surface, it would be 1/100000th of a Newton. Very tiny. You have to have a special equipment to notice this force. But geckos have these billions of hairs which they utilize to attach together to either to the glass ceiling or to the wall, and they work all together. So the idea, I never dealt with animals except the frog before, and bio research is nothing I know about, but I thought this is what I can reproduce using the equipment I'm using for my main line of research. So we managed to reproduce this kind of forest. But the question I ask, if we take graphite, how thin we can make it? It's not an outrageous question. It's like, ancient Greeks invented the concept of atom. They say, philosophers say, let's take a stone and divide into two, and then take a half and divide into two, and so on, divide, until you get to something which is indivisible any longer. So that's they called an atom. And in a sense, this is what we try to do. And how to do this? People couldn't grow thin graphene films, so we use a sticky tape. When you put a sticky tape on the surface of graphite, you get some flakes stick to it, because graphite very easily goes into layers. This is how pencils work, because when you draw a line on the paper, there are these small bits of graphite which are left behind, and they make the pencil trace. So we took this tape, put it twice, split whatever is on the surface, put it again and again. After a few times, you look through the tape, as it is here in a microscope, and what you see here, that some of the flakes are non-transparent, like here, and this is graphite, because graphite is a metal. And you know metal is not transparent, but some of those flakes are transparent. It means that the metal is really very thin. So I know, with benefit of hindsight, I know that it's about 7 layers of atomic layers, 7 atoms. So it's 1 nanometer thick, approximately, 2-3 nanometers thick, without realizing that they probably thrown away their Nobel Prizes as well, and it's happened a million times before me. So why interested in the junk? If you look what you know about the world around us, every object has length, width, and thickness. We live in 3-dimensional world, and all objects are characterized by this one. There is much more to that. There are very powerful that you can't make materials 2-dimensional, or materials which would be 1 atom or 1 molecule thick. It's forbidden. And the reason for this is that you have to use temperature to grow something, and temperature creates vibrations, and those vibrations are not favorable, so the nature tries to make 3-dimensional form to reduce those vibrations. So everything goes from thin wires into some kind of flat sheets here, what you see here. Eventually, when you add more and more atoms inside, it becomes 3-dimensional architecture. And it seems to be impossible to make 2-dimensional materials which would be 1 atom thick, the one which I'm interested in. So obviously we have done this, and the reason is that there is a way around of this one. We know that any material, take for example cooking salt or any other crystal, consists of arrows of atoms and also planes of atoms. So you can grow your material normal way, 3-dimensional way, and then extract an individual atomic plane out of this. And it's not forbidden. This way just was overlooked previously. And it's not forbidden because the material itself, grown at high temperature, in the case of graphite, it's 3000 centigrades, and then you cool it down to our normal environment, which is 300, room temperature, and of course we can use all our powerful techniques like electron microscope here, and you can see the real picture, carbon atoms in this kind of hexagonal honeycomb lattice. So people sometimes ask, so what's so special about graphene? The answer, which I give these days because of better understanding, the most special thing about graphene, its existence. Try to make the same with, for example, gold or copper or whatever material you usually deal with. When you go below thickness of, say, 100 atoms, gold would melt itself. It wouldn't like to be thinner than this one. It becomes islands of a certain thickness. It's also, we live in ambient atmosphere. You try to make even 100 atoms thin copper, and it would oxidize. This material, graphene, is stable down to 1 atom thick. And this would be an interesting story, but it's extremely simple structure. And it's a small part of graphite. And graphite as a material was studied for many decades. So initially we thought, okay, that's it. But then over the next few years, we start studying all the properties of the material and found out that material is completely different from its parent, from graphite as well. And it's, for example, is strongest material ever measured. People claim it. It's the stiffest material. It's stiffer, actually, than diamond. At the same time, you can stretch it as a little bit like a rubber, and it's pliable like thermal conductivity. It's much better conducts heat than even diamond, leaving aside copper. It also allows such high densities that copper would be burnt immediately. It's a very good conductor of electricity, hundreds of thousand times better. So a single layer of carbon, graphene, you can conduct as much electricity as through hair-thick, 1 hair-thick film of copper. So the biggest part we learn that these materials, despite being part of some parent materials, and graphene is one of those, I'll tell later about others, they are very different from their parents because this changes in dimensionality, essentially. The Nobel Prize was given for electronic properties of this material mainly. At that time, very quickly, 5 years later, after everything was first published, we received the Nobel Prize, and it was about, wow, how unusual electronic properties are. And I'll try to give you an idea in my first example of why it's so unusual material, why electrons are so different. Ignore the formulas here. It's just to tell you that usually when we describe materials, like, for example, how electrons move through copper, when you get it from copper mines, subatomic particles behave when they are at speeds close to the speed of light. So graphene gave us an unusual possibility where electrons, those are normal electrons, just like in any metal, but they mimic very closely what's happening with particles when they're close to the speed of light, so-called relativistic physics. So, and this was a big surprise, and this immediately, one of those phenomena known 70 years before us, but people even didn't dream to test it. So is the following. So, you know, all of you have cars, and you know what would happen if you drive in the wall. So this is the world, Newton's world, the world we live. But if you're in a quantum world, for example, electrons in copper or in graphene live, not in copper, no, and other materials live. Some of you probably heard about tunneling. So in this case, a particle has a probability to go through and some probability to be rejected. So that's what we knew, essentially, could test only those phenomena. Tunneling, people believe that this phenomena should exist in near neutron stars and so on, but it was impossible to test it. This phenomena is actually very important for graphene. It's explained, for example, why it's so good conductor, why it's so much better than copper. Because if you put impurity in copper, it stops electrons going. In the case of graphene, those impurities are not noticed by electrons. I'll give you another example how unusual properties of graphene are. So that's completely came only 10 years ago, well after the Nobel Prize, and by that time we knew that graphene is extremely tight. Carbon atoms are so close together that nothing goes through. It's completely impermeable. And there was also known a material called graphene oxide, which makes nice laminates. This kind of brick structure, which consists of individual layers of graphene, but it's very easy to make this material. You can make square meters, square kilometers if you want. So in one of those experiments which led to a lot of further work, we said, oh, all right, we know that individual layer is impermeable to anything, like gases, and helium is known as most permeable of all gases. It doesn't interact. So if we make this brick wall consisting of graphene atoms, it would be completely impermeable. And yes, we tested it. It was completely impermeable for helium. We tested many other gases, and then, just in case, put water inside and found something strange. Water not only easily goes through, if you heat it up, you see steam coming out there. No barrier at all. So it's kind of an oxymoron. On one hand, it's impermeable to most permeating gas, helium. On the other hand, it's super permeable to water. How could it be? It tends to be this material, graphene oxide, is very intelligent material. Feel those capillaries, and then water goes very rapidly, quicker than water flowing through your tap, goes through this film and evaporates. But then if you remove water, immediately those capillaries automatically shrink, and this kind of shrinkage does not allow even helium goes through. So the material is extremely sensitive for the water, intelligent material, like a nose. If water is there, I'll let you through. If it's dry environment, like in Atacama Desert, nothing goes through this. Very unusual for a physicist. My final example about graphene, again showing how difficult it is about came a couple of years ago, even less, maybe a year ago. So you know what the Philosopher's Stone is, not from Harry Potter, but people, alchemists, try to turn lead into gold. Graphene allows something like this. So in our case, instead of lead and rubbish, we use electronic rubbish. So this is where your computers, your mobile phones, where they end up. So what we did, literally take this kind of rubbish, dissolve it aqua regia. It's a mixture of nitric and chloric acids, I think so. Have forgotten now exactly. Chloric and nitric acid. Dissolve it, got this liquid, and now we pour this liquid in real time through a filter which contains many of small pieces of graphene. And you see what's going on. It becomes yellow. And what we have found that we can extract only gold, everything else goes through. with extremely high efficiency and extreme selectivity. Copper, nickel, anything else, all other ions going through. So this gold is easily taken out. You burn this filter using your kitchen flame and you get a real gold out of this rubbish. This is, I don't know whether it will ever be used because aqua regia is a little bit expensive to deal with. It's question of economic cost, but this gives you an example that if you do the same with graphite or even 5 layers thick graphene flakes, it won't happen. How different graphene is from graphite. Graphite doesn't feel anything. It's the most inert material possible, while graphene is catalytically very active. It allows to convert ions into neutral metal gold. So this area of research, we knew practically everything already more or less about physics of graphene 10 years ago, and Nobel Prize was kind of a milestone, and people start looking what else can be done. Usually research goes very quickly up and then slowly decay. And everyone, in 2007 I wrote a review about graphene after 3 years of research only, saying graphene is dead. Long live graphene. And it turns out to be true, because we also knew already at that time that graphene is not alone. You can't make gold or copper one atom thick, but there are many other materials. We already demonstrated a year after graphene, we already demonstrated about dozens of different materials, and now we know approximately 5, maybe even 500, maybe even thousands of different materials. And obviously, if graphene is so unique, people looking what else, what kind of applications or new science other materials can bring in. It's a very intensive research in condensed matter material science. Turns out to be graphene is really unique, but sometimes it's too conductive, flexible, and so on. It requires to scale up this, which is not easy, but people working on this one. So microelectronics industry is interested in this kind of research. During the last 5 minutes or so, let me discuss what it is good for. The Nobel Prize was for physics, even not for material science, okay? But people want to know what physicists and so on are wasting taxpayers' money at what kind of research. So because it's so unusual material, people start thinking about applications, but all kinds of applications. This transparency, this slide is 15 years old, what people have thought at this time. And there are hundreds and hundreds possible applications people discuss in literature, and I don't have time even to overview every one of those would require 5 minutes, and there are hundreds of those. I'll give you an example what you can buy these days where graphene is used. It improves, it's composite material. It improves quality of plastics, making them tougher, making them a little bit more elastic, making them thermally more conductive and electrically conductive, and so on. And there are many applications. I probably have 10 different slides about this, but if we stick to this slide, if you have a lead acid battery, not lithium battery like in modern cars, but a normal petrol cars, and if it's made in China, then for sure it will contain graphene as a part of its lead electrodes. It improves efficiency, something by 10%, improves quality of those. This probably most impressive example I learned about half year ago, that this is street light LEDs, and the company uses graphene on the back to cool those LEDs down. So the company goes to a local government and say, you have your streets illuminated by LED devices. We'll make for free completely new LED lighting in your whole city for free. The only thing we want is the savings in electricity for the next 10 years. So that tells you that savings in electricity due to cooling by graphene makes LED much more efficient. I know that near Antofagasta that there are many solar farms. I don't know how modern they are in terms of efficiency, but if they are only a couple of years old, and if they are the solar panels bought from China, most probably on the back of those solar panels there is graphene paint which covers it. What it does, it improves efficiency of solar cells. Degrees or so cooler, and this increases efficiency dramatically by 10-20%, which is an extremely worthwhile cost put in. So, but this is kind of where graphene is put, but yeah, it requires scaling up. It requires to compete with silicon industry, but hopefully in 10-20 years we'll get this transparent. This is a little bit, of course, futuristic, but kind of what is on this, for example, slide, transferable, bendable and transferable electronic. This is certainly possible. That's the end of my talk. In terms of science, material science, condensed matter, it was a true revolution. It's reshaped completely. People were dying of boredom, what to do next in some of those areas, and it's extremely good. In terms of applications, it's probably too early to expect much, but we have already hundreds of products already existing, and hopefully it will go further on. Even in Antofagasta, I know there is a company which tries to use graphene to make more efficient electrodes to extract copper. So let me finish my talk with this slide. So as I told you, this is how pencil works. The world around us, that there are many more discoveries to be made. With this, on this note, let me finish this talk. Thank you.